Good evening, everyone. I hope everyone has been enjoying the Astronomy at the Beach virtual event so far. So we're getting near the end of the event, and we're about to go. We're about to start another session with our main speaker is going to be Tim Campbell, and I'm going to be his not so beautiful assistant. And this presentation is going to get a bit sciencey, and we're going to be talking about spectroscopy and how scientists use light to discover what the universe is made out of. Now, as always, please feel free to post your questions in the chat. We will answer them as we go. We have two more events following immediately after this. One is going to be John McGill is going to be talking about taking photographs of NASA space launches, because he's a certified photographer with NASA. And immediately following that, we're going to have Gordon Hansen talking, well, depending on the skies, they don't look good right now, but going to do possibly live observing from Woodhaven here in Michigan, or if not there, he's going to be showing us how to stack images taken during astrophotography sessions that he's done himself and process those into beautiful images. So without any further ado, I'd like to turn it over to Tim.
All right, thank you, Liam. As we get ready to start this, there's going to be several interaction points for you. And one prop that I'd like you to grab, if you can find one, is go find a Lincoln Head cent, just 1 US penny. This will come in handy near the end of the presentation. You'll see why. So if you can grab one of those, and Liam may be partway through, if you can remind people when we take a breath that if people join late to grab a penny. All right. So let's get started because we've got an awful lot to cover. I'm going to go ahead and share my screen. And there we go. All right, I'm now sharing, and I'll make this full size here. There we go. All right, so this presentation is a combination of actually just a few things. So to understand the spectroscopy, there's a couple other things that I kind of want you to understand a little bit first. And so with that, this is a quote from Carl Sagan. He says, "If you wish to make an apple pie from scratch, you must first invent the universe." What does this mean? Well, if you're making an apple pie, you're probably coming equipped with things like flour and butter and apples and sugar. And the question is where did the sugar come from? And where did the butter come from? Well, those are made up of other elements. And where did those elements come from? And so that's what we're going to talk about when we begin. And so one of the things that I want you to see is just this little thing on how stars form. This is just a little snippet that I'm going to show you. This is Dr. Don Pettit. He was on the US Space Station. So we've got the International Space Station. And I want you to see this little video clip here. What he's done is he's taken a bag. This is just a plastic bag. He's on the space station and he threw salt in the bag to see what would happen because he's in this zero gravity. It's not really zero gravity. It's a microgravity environment. And notice, if you will, that these pieces of salt are actually clumping together, and then he shakes them apart, and within a few seconds, they come together. And this is something that's very interesting because the formula for gravity is you got to know the mass of the two objects and the distance between them. And it turns out bits of dust are so small that it turns out there's so little mass that almost no distance between them. They have virtually no gravitational pull. Why would they ever come together to begin with? And what he's finding is that essentially static cling is doing the trick, right? So these things have an electrostatic charge. Now, when you pull your salt shaker out and shake a little bit of salt on the table, it doesn't seem like they're static cling. Well, that's because the Earth has so much gravity that the gravity is overpowering that static cling. But hey, in a microgravity environment, static cling wins when we eliminate the gravity. Now, he does the same experiment again because he says, yeah, what if it's something special about the fact that I use salt? So I think he uses sugar, he uses ground up tea leaves, I think he used coffee grounds, he used whatever he could get his hands on. And it turns out it didn't matter what he used, they all do that clumping. Once you get enough of that clumping going on, now you start to actually have some mass. Now you actually start to have gravity, and eventually you can make a star. So I've got this little video clip that I'm going to play for you here. This is just a photograph of the Orion Nebula. This is a nebula that we normally see in the winter months, like December, January, things like that. Now we're switching to a Hubble ESA photo. Again, this is Hubble. We're zooming into the core of the galaxy. I'm sorry, the core of the nebula. This is a star-forming region. Lots and lots of stars are made here. It's where stars are born. It's one of the star nurseries in the universe. But that's not what we're after. We're going to pan around and we're after something else. And there it is. This is our prize. This little black speck on the screen. And if you're scratching your head wondering what the heck this black speck is, that's a really great question. This is a protoplanetary disk. That little glow that you see in the center of that black smudge, that is a star, a little baby star being born, and that black cloud is actually sort of donut shaped, and you're looking at the donut on edge. And that black cloud is going to turn into the planets. And it's not just that one. When we detail it, you can see there's another one up here and another one over here and over here and over here. And so Hubble took all of these images with incredible resolution. So all of this was really just a theory of how stars would form, or I shouldn't say a theory, a hypothesis that and all the math worked out well, but we'd never actually seen it. Well, now we've actually seen it. So we actually know that this math is actually correct. Now it takes a long time for these stars. It's not like, you don't build a solar system in a week. So it takes millions of years for these things to form, but in fact, it does actually work. All right. So where did all this stuff come from? So what is in the universe? So here's a periodic table, and if you've been into any kind of a chemistry class, you've probably seen one of these. I've really simplified this periodic table. I've also animated it. But each element has a number, and that number indicates the number of electrons that atom has. So hydrogen has just one electron, and in its nucleus, there is one single proton. In there as well. Now, in a normal hydrogen atom, it's just one proton, just one helium. There could be a neutron, which has no charge, and that would be fair too. It turns out that does happen from time to time, but not very often. But that is element number one. Over here on the right, we have helium. It's element number 2. It has 2 protons and 2 electrons. And then element number 3 is lithium. It has 3 electrons and 3 protons, and so on and so forth. So the numbers are actually telling us how many electrons the atom has. So if this is the chemist table, though. This is not the astronomer's table. So if I take away all of the elements that astronomers don't see when they study the rest of the universe, or at least they hardly ever see, it's hard to detect it, this is what you have left. And we're going to cross out the word chemist, and we're going to put in the word astronomer. This is the astronomer's periodic table. This is what astronomers see through telescopes when they look at stuff, mostly. Now, most of what they have is not equal quantities. Mostly what they find is hydrogen in abundance. About 90% of all ordinary matter in the universe turns out to be this hydrogen. They also see helium, about 10%, and all those other elements combined, less than 1%, not very much of it. And that is what is in the universe. And the question is, how did we get it? Well, one of the other things that's kind of interesting is this little thing that talks about the abundances of the elements. Now, this is a logarithmic scale. That means each time you cross another blue bar, that's 10 times as abundant as the bar below it. And you'll notice it's zigzagging up and down. Pretty much every other element is zigzagging up and down, and that's kind of curious. I've shaded the top of this green, and I've shaded the bottom of it with this sort of reddish color. And that's because the green zone, those are the elements that astronomers tend to see when they study the universe. And the red stuff is the elements that they don't tend to see through telescopes. Now, obviously, we know these elements do exist because we find them here on Earth. AU, way down here, element number 79. AU, that's gold, right? We have gold, not a lot of it. Look, it's way down here, low, so it's not a very abundant element. All right, so how are they made? Well, we started the universe with the Big Bang, and the Big Bang actually didn't create any elements initially. There wasn't even any matter initially. It was just energy. And then through interactions with the Higgs field and the Higgs boson, particles started to get created, particles that actually had mass. But those particles could not form together to make any atoms because the universe was way too hot. It was blowing the, if you had an atom, it would have blown it apart. And so, but as the universe started to expand, it started to cool. And then there's this magical point where it's hot enough that helium atoms could fuse, but not so hot that it would take them apart. And helium is formed. Those helium atoms were able to make a little bit of hydrogen and also a little bit of lithium. So you got hydrogen, you got helium, and then they argue maybe a small amount of lithium, not a lot, but a little bit, not zero. And that's it. Nothing else. That's all there is in the universe after the Big Bang is done. Chemistry class is a breeze. However, that was the Big Bang. So now we know that we have a universe that has hydrogen, helium, and lithium, and that's all it has. The next question is, how are elements made in stars? So there is this process called, instead of Big Bang nucleosynthesis that made those first three elements, this is stellar nucleosynthesis. This is how elements are being synthesized out of stars, using one base element and turning it into another. And stars do this all the time. So if we take a star like our sun, 90% of its life is going to fuse hydrogen atoms together and turn them into helium atoms. Now, it's a little bit lengthy to talk about how this works, but I'm just going to do a quick demo here. I've got a can of compressed air dust, electronics duster. And if I'm holding the can, it's just at room temperature, and I just blast the nozzle for a few seconds, and I touch the can is now cold. That's because if you decompress a gas, it gets cold. If you take a gas and you compress it, it gets hot. Oh, by the way, this is why your refrigerator works. It's how your air conditioner works. They're just being very strategic to compress the elements so they get hot, or compress the gas so it gets hot when it's on the outside of your house, blow it through a radiator for a while with a fan to kind of cool it off, bring it back inside the house and decompress it so now it's extra cold, and then blow that nice cool air on through the house. But in a star, that gas is just getting compressed and compressed and compressed and compressed, and there is no radiator to cool it off. So what happens is those atoms, they are getting hotter and hotter and hotter, and the heat is a measure of how fast they're vibrating. And if they vibrate fast enough, and when they hit each other, instead of knocking off and bouncing away, they break each other. So it's like if I take a tennis ball and I throw it at the wall gently, it bounces off. But if I could take some kind of a gun and torpedo it at the wall, the tennis ball might actually break. There is an energy level at which the collision causes things to shatter instead of bouncing off. That is what's happening in the heart of the star. After it's done fusing the hydrogen into helium, the helium can then be used to fuse into carbon. Now you notice I have lithium still on there, that's left over from the Big Bang. You do see a couple of other elements that I've shaded out. It's because I've kind of bypassed those. You'll understand why in a few minutes. Really what the star is doing is every other element, carbon, and then the next one that it can fuse is oxygen. And again, I've shaded off the ones in the middle. Because our star doesn't actually make those. Those get made by side effects processes. I'll talk about that a little bit later. And that's it, nothing else. Our star isn't massive enough to fuse any element heavier than oxygen. Most of its life, it's just going to fuse hydrogen into helium. And that's what it's doing right now. It's not making any oxygen. The reason it's not doing that is because you need about 15 million degrees Kelvin to heat the hydrogen hot enough to turn it into helium in the first place. To turn helium into something heavier, you got to have almost 100 million degrees Kelvin to do that. And the core of the sun isn't hot enough yet. But when it runs out of hydrogen, the star will lose its energy and gravity will start to win. That star will start to collapse again. It will squeeze even tighter. That will drive the temperature up and up and up until it is hot enough to fuse helium. And when that happens, helium starts to fuse, the whole star swells up, it gets much hotter, and it's also hot enough to fuse even more hydrogen that was on the outer part of the star that was not accessible before. All right, so now, here's a very simplified view, not super accurate, but we're trying to make this easy for how all the other elements are made. So again, we're skipping over every other we're skipping over every other element on the periodic table because it turns out each element is created by slamming into that element something called an alpha particle. And what's an alpha particle? If you take the nucleus of a helium atom, that's 2 protons and 2 neutrons, that clump of 4 things, we call that an alpha particle. And if you slam that into one of these things, you make the next atom, not the next atom over, the next 2 atoms over, because you added 2 protons to it. Now you have to add 2 electrons. And so that's why it's doing every other element. Okay, once you've done that, I'm gonna go ahead and let, Ani is joining there, Liam. So once you've done that, I've gone ahead and filled in the byproduct elements. So now those are filled in. The star makes it all the way up to iron, Fe. Once you get to iron, it's kind of curtains for the star. Stars have probably minutes to live by the time they get to this stage. And at this point, a supernova explosion can happen. This is only the most massive stars. Our sun isn't big enough to do this. And then you can get pretty much the rest of the periodic table. Now, I did warn you that this is a really oversimplified view. It turns out many of the elements in the periodic table are actually synthesized, and stars don't even make those at all. So things like gold can only be made in these supernova explosions, and only for a few seconds. Now I'm dropping these little circles onto my periodic table. These are the major elements that your human body is made out of. But what I want to call your attention to is, remember, the Big Bang started by giving us some hydrogen, some helium, and some lithium. It did not give us any carbon. It did not give us any oxygen, right? It did not give us any magnesium and so on, no potassium. But you need these things to live. All of these were synthesized from stars. You also need some trace elements that can only come from supernova explosions. So for example, we have iodine out here. You need a tiny bit of that to be able to live. Not a lot, but you do have to have some. In fact, because of some iodine deficiencies, the salt companies will make a product called iodized salt, because it turns out it's easy to get iodine to bond to salts, and that makes up for iodine deficiencies that you might have. And those are the trace elements. But the main important point to take away here is that if those things aren't here, you're not here. And the way that those things got here was through these stars. So you are literally made out of this star stuff. Now, this is a different view of the periodic table. This one has all kinds of different methods and talks about how the elements get created. You know, some of those byproducts are decay. Some of the byproducts are fission and things like that. And you can actually find lots of variations on this particular periodic table. But that's just a sort of the short and simple version of how it is that all of these elements are made. And this is going to tie into the cool stuff with spectroscopy coming up. And so here's a quote from the late Carl Sagan: "The cosmos is within us. We are literally made of star stuff. We are a way for the cosmos to know itself." How poetic. All right. By the way, after those supernovas blow up, they leave behind something called a supernova remnant. This one is not my image. This is someone's image of the M1, the Crab Nebula. And if you look at it with a radio telescope instead of a visual telescope, what you see is this thing called a pulsar. So a very tiny, super compact star, but it had to conserve its angular momentum. And so this little tiny thing is spinning so incredibly fast that it cannot give off its energy evenly, and it sends it out as pulses. And some of these things click at an amazing rate. All right. So that's the thing about star formation. Now let's talk about light. And when we get into talking about light, one of the things that I want to talk about, we're going to talk about the various gases, the elements, and how they give off different spectra. That is the whole point of this presentation. But before we get to that, it's important to understand this little concept here. So I've got these three stars, exaggerated color stars. I've got a red star, I've got a yellow star, I've got a blue star. But what's more interesting is these little graphs above the star. So I've got this whole rainbow up here that I'm showing. Above each star, there's a rainbow, but there's also this bell curve. And this is not spectroscopy per se. This is something called black body radiation. So in other words, if it's hot, it gives off energy just because it's hot. So if you are a blacksmith and you want to make something in your blacksmith forge, you take your piece of iron, you put it in the fire, You pump the bellows, you get the fire really hot, and you get it so hot that that iron is glowing red hot. Now, it's not glowing because iron gives off orange, it's glowing because it's hot, right? So the logs in your fireplace, if you light a fire, they are glowing yellow and orange just because they're hot and they're not made of iron, right? So that's an example of black body radiation, but that's black body radiation inside the visible spectrum. We can see that, but there's a lot of energy given off on the infrared that our eyes can't even see. So these red stars are giving off mostly infrared. And they're giving off a lot of energy in this red side of the visual spectrum here, but they're not really giving off much on the blue or purple side. And so this star is decidedly a lot more red than it is blue or purple. When we get a yellow star, it's right in the middle. And so it appears yellow, kind of halfway in between. But we get to this blue star, it's very high energy star. So it's giving off a lot of energy even in the UV side of the spectrum. And when it gets into the visible side of the spectrum, you see these purples and blues coming out. But look, when you get down to the reds, not so much. It's not giving off as much energy at those particular wavelengths. And so this is black body radiation. Now everything gives off black body radiation. The chair you're sitting on is giving off black body radiation. You are giving off black body radiation, right? You show up in a thermal camera. If you go into your freezer and take out an ice cube, that ice cube, cold as it is, that's also black body radiation being given off by the ice cube. It's not at the temperature of absolute zero. So while you think, hey, this ice cube is probably around 0 degrees Fahrenheit, right? But there are things in the universe that are much, much, much colder. And so if you were standing on Pluto and somebody offered you that ice cube to warm up, that might be a welcome gift, because compared to the temperatures on Pluto, that ice cube that just came out of your freezer is pretty warm. So all of these things are black body radiation. All right, and now it's time to get into the fun stuff. This is the whole point of why you came, and we're going to do a little bit of a demonstration. Now, before I do the demonstration, I'm going to stop my share.
Let's show your spectroscopy glasses first. They're diffraction glasses.
All right, so if you were to come to the planetarium and we were going to do this, we would hand everybody in the room a pair of these glasses, and you would put them on and fold them around. If you would actually like to own a pair of these, they are actually very inexpensive. These are from a company called Rainbow Symphony. You can go to rainbowsymphony.com. I bought them on amazon.com, and I buy them in bulk. If you do decide to buy a pair of these things, very important, what they're made out of is lots and lots and lots and lots of prisms. In fact, 500 prisms per inch. Now, the grooves on those prisms are so incredibly fine that if I were to take my finger and touch the surface of this, that my skin oils would fill in the grooves in the prism, and these would actually stop working. So if you do decide to get your own pair, careful not to touch them or they will stop working.
Wait, Tim?
Yeah.
That's not a diffraction grating. That's a diffraction grating, right? None of those small little things. This is how you do it. You go big or don't go at all, right?
Yeah. So the reason that Liam has that diffraction grating is because these do not fit on the front of cameras very well. Cameras don't have noses on them. So we made that giant pair that Liam is about to demonstrate to you. By the way, before you do that demonstration, I was just going to remind everybody, again, if you're joining late, grab one of these pennies. You'll want this near the end.
Okay. So you want to bring up the plain light first? You want to show that one before we go?
Yeah, I can do that.
Yeah,
so
reshare your screen.
I'm going to reshare my screen, and let's see, sharing the right desktop, and hit the play button. Okay, and there's our demo. And what I wanted you to see, this is an ordinary incandescent light. I know some of you young people say, what's an incandescent light? Because everything's an LED now, but this is not an LED. Inside this glass tube is a tungsten filament. It just gets really hot, and it gets hot enough that it starts glowing. It actually gives off a lot more heat than it does light, but this is how we used to very inefficiently light our homes once upon a time. But this is in here because it's just a simple source of black body radiation. And so I'm going to give you this quick demo, and then we're going to have Liam show you what he's going to do. If I slide this over, This was pre-recorded earlier because we thought that it might be difficult. This is that diffraction thing that Liam was holding up, and we're holding it in front of this light bulb. And what's going on is you see a complete rainbow color. It's solid all the way through. You see these weird wiggle lines. There's actually little things inside the glass tube that you can't see because it's so bright that are holding the filament from time to time, and that's what those little gaps are. It's just how they constructed the light bulb. So that is just what happens when you put something hot with the diffraction grating in front of it, so you can see what that looks like. Now I'm going to go ahead and stop that. I'm going to stop my share.
Okay, and pin mine, please.
Yep.
So I just switched over a camera to a different camera, so we have a different point of view. So you see here we have a tower with white light on the top, going all the way down to a violet colored light on the bottom. So the violet is the more higher energy, and up towards the reds and so on is a lower energy. So if you put the diffraction grating in front of this series of lights, you will notice that the lights get broken up. But let me see if I can get closer. You see the way the lights are scattered along the side here? This actually, the diffraction grating scatters the light, so you can actually see what the different types of light are made out of. Now, I'm going to go to individual element lights in a brief moment. So let me turn this one off. And this is going to be a bit noisy because the hydrogen and gas tube is a bit noisy. So the hydrogen gas tube, as you can probably hear a buzz in the background. Oh, focus is gone. My focus has gone out.
Yep, we're trying to get it back.
There we go. Maybe. Now, when we do hydrogen, you can see the different colors being broken up by the diffraction grating. Once we know this, once we see the, oh, it doesn't like the.
It doesn't like that.
There we go.
There you go.
Now, so we have you see the different colors created? So we're actually scattering the light. And now these light beams are the light bands you see that colored all the way over to one side. This actually is the light spectra of hydrogen gas. So we know what hydrogen gas looks like when we divide up its light. So the next one I'm going to show you.
And you'll get a more detailed view of that in just a moment. It's a little difficult to see the video that he's doing, but I'm going to give you a closer up view of that.
So here's another one, another type of element. It's an excited gas in the gas tube. And when we excite that gas, you see the difference in the colors. We have a lot more colors showing up over here to one side. So we actually have a more variation of the colors, and we'll explain why in a moment. So this element is helium, is what you're seeing, helium gas excited. And I have one more to show you, one that you see on a regular basis. We've all seen these neon lights. Now this is really, really bright. Let me see if I can adjust this setting down one fraction, because it's
it went off completely.
Just turn off this setting, because the camera is better with low light. So we have, this is neon light. When you look at neon light, you see all the way over to one side, you have an awful lot more colors showing up, all the different bands. Now, we're going to explain in a moment, or Tim will show you in a moment, but it's to do with the complexity of the atom, why there's more and more colors and more separation of the colors as we go through the various heavier elements.
Sure.
So do you want to go back to your presentation, Tim?
Yeah, let me cancel your spotlight, and I'm going to go back to my presentation, reshare my desktop, and resume where we left off. Okay, so we pre-recorded these earlier to make it a bit easier for you. This was that LED tower, and what we really wanted to point out was that the redder the color, the longer the wavelength, the more it shifts over to the right. The bluer the color, the shorter the wavelength, the less it shifts over to the right. And that's the whole purpose of the spectroscopy. All right, and here's the hydrogen tube again up close. This is just, and you can see it looks like this pinkish, purplish, bluish thing. But if I grab this and speed this along here, there we go. And now you can see here, this bright red color here, that color is called the hydrogen alpha color. So if you saw Ani earlier doing his solar telescope thing, that was a hydrogen alpha solar telescope. only this particular wavelength of light is what that telescope was looking at, and all the others were black. There's also this bright teal blue, this violet. There is actually a fourth color that isn't showing up due to the sensitivity of the camera. All right, and now here's the helium, and this sort of looks like this yellowish peach kind of color. But again, we slide over to where Liam puts the diffraction on it. And now here you see this nice close up. Far to the right, you see the red. You see this very, very bold yellow. It's very bold, and that's why this thing in the middle looks mostly yellow. And then you see a couple of different very thin greenish teal blue bands, and then a deeper blue sort of indigo, and then a violet band there. And then the last one that we have for you is the neon one. And again, I will slide over to where Liam puts it. And this one has a crazy number of colors in it when we look at it, but they are mostly reds, yellows, and oranges. And yeah, you see these greens, but just a couple of them out here, not enough to significantly change the color of this. And that's why when you look at a neon light, when you've seen like a commercial business and they have neon signs in front, it's that particular color. But when we put the diffraction grating, it pulls it apart. All right, so with that, here's how this works. So now we're getting a little closer to the science of it all. The visible spectrum is roughly 400 nanometers on the blue end to about 700 nanometers on the red end, but you'll notice that my numbers aren't 400 and 700, they're 4,000 and 7,000. That's because while we could talk about this in terms of nanometers, a nanometer is 1/1000th of a meter. It means if you went and grabbed a meter stick, divided it into 1 billion sections. If you had something that was a 1 nanometer wave, that means it would be only one of those nanometers long. But if it were light and it were at this 400 nanometer end, you'd have to count 400 of the nanometers on your billion nanometer meter stick. And that would be the length of just one single wave. So these red waves are longer than the blue waves. These are shorter waves, and these are more energetic waves. These are because they oscillate more times per second. And the red ones are longer. They oscillate fewer times. They repeat fewer times per second because they have less energy. And then the angstrom is simply 1/10 of the nanometer, and that's why we can just add in a 0. So hydrogen corresponds to these colors that you saw, but the brightest one that it puts out is this red one. When you looked, you saw when we put the diffraction grating, you saw the red one. You also saw this blue one because it's also pretty bright. You didn't see these 3 fainter ones because the camera didn't have enough sensitivity, but a more sensitive camera would have revealed those. Okay, and then a helium, which I simulate with this kind of yellowish, peachish sort of looking color here. But this one has more different color bands. So these are like barcodes, except they're colorful barcodes. But the most dominant one by far is this particular yellowish, orangish color that appears here. The others are more faint. And then we got to neon. And it had those greens that you saw, but mostly what you saw were these yellows, oranges, and the reds off to here. But I've numbered these elements. So this is element number 1, hydrogen. And it has 1, 2, 3, 4, kind of 5. This is technically in the UV, 5 lines that it's giving out. Helium, 1, 2, 3, 4, 5, 6, 7, 8. It's faint, 9. 10, actually I see 11, right? So a lot more lines coming out of helium than hydrogen, but this has 2 electrons. This only has 1 electron. But this neon one, this has 10 electrons, and I get a crazy number of lines. In fact, if I really zoom in with this, I would see that many of these lines that I think are 1 line are actually many lines. So what's going on here? The more complicated the atom, the more electrons it has. The more electrons it has, the more possible things those electrons can be doing, and that causes a more complicated spectra to show up. And so here is the geeky part of the science. We consider that these electrons can have energy levels to them. I'm depicting this as a series of rings or tracks, but there are many ways to think of how they might be depicted. When the electron when the atom absorbs energy, the electron will be lifted into a higher energy state. So for this is a hydrogen atom, its rest state is this number 2 ring here. It gets lifted into this higher energy state. And then for some reason, and it will absorb light when it does that. But it will only absorb light of a particular wavelength, and that wavelength is the hydrogen alpha wavelength. It has to be 656.28 nanometers. That's what it wants to absorb. It doesn't want to absorb anything else. Any other light hits it at any other wavelength, it just flies right on through, well, except for these other ones that I'm about to draw. And then there are a few other wavelengths. So once it absorbs, the atom goes into a higher energy state, and then it turns around and gives that energy off, re-emitting that photon back out at exactly the same energy level that it absorbed. And so when it's absorbing light, if you had a black body light source in the background, the absorption would be revealed as little gaps in the spectra. And that's why I'm sort of showing you this absorption spectrum at the bottom. But if I were to energize it and there is no black body source behind it, it would emit. And so you would see this thing called the emission spectrum. That's what you were looking at with these gas tubes, is called an emission spectrum. But when we look at the spectra of the sun, we're mostly looking at the absorption lines. These are also called Fraunhofer lines, from Joseph von Fraunhofer, who discovered them when he took the rainbow color that a prism would give of the sun and took a magnifying glass to it to really inspect it closely and said, wait a minute, this is not one solid color rainbow. There are little gaps in it. In fact, when he did that, he realized that there were actually, well, once he did that, they realized that they should start playing with these elements by putting them in a Bunsen burner in a flame to see what colors they give off, while analyzing them through a spectroscope to see what the little colorful barcodes look like. They do this, and they realize that if they put 2 things in at the same time, the spectra is actually just both barcodes added together. So in other words, you could overlay, if I put, so we showed you a hydrogen gas tube, a helium gas tube, and a neon gas tube. But what if we would have put the neon and the hydrogen and the helium all in the same gas tube and turned it on? Well, you would have just seen all of the barcode colors all overlaid at the very same time.
Tim, we have a quick question.
Yeah.
Arnie's asking, what is the difference between hydrogen and hydrogen alpha?
So hydrogen is the name of the atom, and hydrogen alpha is one of the wavelengths in what is described as the Balmer series. That is the absorption and or emission lines that particular atom is willing to absorb. And so, fun fact, why can you see through glass and you cannot see through walls? And it turns out, and it's also, gamma rays are photons, X-rays are photons, radio waves are photons, light waves are photons. They're all photons. They're just photons of different wavelengths. And so it turns out radio waves go right on through your wall like it isn't there. Maybe a little bit of a radio loss, meaning that some of the photons were being absorbed, but most of them, hey, they sail right on through, because you can talk on your cell phone while you're inside your house. You don't have to go outside. If you walk inside and close the door, it doesn't hang up the call. That's because the radio waves are sailing right on through the wall.
Unless they're in your house, Tim.
Unless they're in my house and you live in my neighborhood. So that's because those walls are not made out of elements that want to absorb those particular frequencies of the radio waves. That's why they use those particular frequencies for the radio waves, is because it will go through those objects. So if you were a radio wave, your house looks like it's mostly made out of glass. It looks transparent to those photons, and it sails right on through. Now, we humans, with our limited vision in the visible spectrum, turns out glass is made out of certain elements that vary. I mean, if you had a piece of glass thick enough, you would realize that the glass is probably just slightly foggy. It's not absolutely clear. Does it absorb some photons? Yes, it does. But hey, a lot of the photons sail right on through the glass if it's a thin piece of glass, because that glass is not interested in absorbing any of the photons out of the visible spectrum. So they go sailing right on through. So that means that glass is transparent to visible light photons, and that's why we can see through it. You know, if we could see in X-ray vision like Superman, or we could see in radio vision, we would be able to look right on through the walls like they weren't there. Of course, we would also be looking through people. So, you know, people would be invisible to us too, because radio waves can go flying right on through our bodies. All right. So you can think of those light waves or radio waves or all the photons as being like sound waves, right? If we change the pitch of a sound wave, the pitch is higher or the pitch is lower, depending on the wavelength of the sound wave. And if we do the same thing with light waves, the pitch is higher, it will shift toward the blue side of the spectrum. If we make it longer, it will shift toward the red side of the spectrum. It shifts colors for our eyes. So here's just a little diagram of the Doppler effect, that if something is coming, so we have an ambulance in the middle, so we all know what ambulances sound like. But when the ambulance is racing down the road, when it's coming toward you, the siren has a higher frequency pitch. And when the ambulance goes whizzing on by, the sound bends, and all of a sudden that high pitch oscillation that it was making turns into a low pitch oscillation. And that's because of this thing called the Doppler effect. The radio waves were always being transmitted at the same frequency by the ambulance, but because the ambulance was coming toward you, radio waves being transmitted were piling up on top of radio waves being transmitted, and they're all not very far apart, and your ears hear that as a higher frequency pitch. The same thing happens with light. So when things are coming toward you, here's an example of a star, and I've got a massive planet orbiting the star. And so now I've got the star is moving away from us, and the radio waves are stretching. Now it's coming toward us, and the radio waves are compressing. I shouldn't say radio waves, the light waves are compressing. And so we're watching this star oscillate from high frequency to low frequency. And that tells us that this star is being thrown around by something that seems to weigh a lot, but we can't see the something that seems to weigh a lot. But we can kind of infer that there must be something out there. We can figure out what the period is, roughly what the mass is, and bada bing, bada boom, we can figure out we got a planet. All right, so here I've got a simulation of the stellar neighborhood, stars within 200 light years, all identified by Hipparcos. Hipparcos was doing this originally by doing parallax measurements as we go around the sun, and it doesn't have to put up with the fact that the Earth has an atmosphere that's messing with it. I've also, now I've got Kepler, NASA's Kepler satellite. Kepler is looking to see if it can find planets that have, stars that have planets. Now it is using the eclipsing method. It's not using the spectral shift method to detect the stars. Yeah, right. So it's not doing that. Kepler, by the way, ran out of some of the fuel that it needs to operate, the coolant, and is no longer able to operate. It's now been replaced by another satellite called TESS. But these are using visible, transiting method to detect planets, but we can also detect planets via spectroscopy.
Well, before, just to give a quick example, by using the transit method, they're looking for a planet to pass in front of a star and measure the dimming of the star. At this distance to the stars, it's like you here in Michigan looking at a flashlight in California and looking for the dimming of a mosquito passing in front of that flashlight. That's how sensitive they are.
So I want to talk a little bit about, we've sort of given like the planetarium version of spectroscopy a little bit. I'm not quite done yet. But we haven't turned this into an astronomical application yet. I mean, we gave an example of one with the star, detecting a planet via this thing. But I'm going to light up this software called Realtime Spectroscopy, RSpec. And I'm going to light this up, and I just want to bring up a sample star here. And I think it's already open. I'll just make sure it is. Okay, so on the left, let me slide this window way over here. Okay, this is what happens with the camera. And actually, before I do this, I'm going to stop sharing my screen so you can see my video, because I want to show you a gadget. So remember, I showed you the glasses, and Liam showed you the great big version that we put in front of the gas tube. But this little guy here, this is sort of what we would put on a telescope. And the way we put it on the telescope, it's the same kind of diffraction grating. This is an amateur grade one. This is not what the professionals use, but this is a camera. It's a little monochrome camera. It turns out it's much better to use a monochrome camera than a color camera. You'd think, well, are we trying to find color? It's like, yeah, but what we're really trying to find is how far we bent the light. It's a distance that we're trying to find. So I take this little thing, I screw it on to the front of the camera, and now I can take the camera, slide this into the back of the telescope, and I've now turned my telescope into a spectroscope so I can image stars, and I will get an image that looks like this.
So while Tim is doing that, just remember, we got about 10 minutes or so left, 10 or 11 minutes. So if you have any questions, please get them into the chat so we can address them as we go.
All right, so here is my software again. So when I take that picture with this little camera, what I get is this little point of light here. That's what we call the zero order point. That's the actual star that I'm imaging with the spectroscope. But off to the side, we get a smear. We don't get a barcode. Remember we said it was going to be a colorful barcode? Well, there's a lot of elements in a star. We're not looking at just one or two elements only. So they all smear together. Well, when they smear together, what we're going to do, I'm going to slide this back over to make this the biggest thing. You notice that I've got this big peak here, this big spiky thing. This corresponds to this point of light right here. And then I've got this thing that looks like a mountain range over on the right. It starts out low, it gets high, and it ends low again. Well, that is this smear here. It starts out dim, it gets very bright, and it gets dim again. And so that corresponds. But you'll notice that the label across the bottom says pixels, and that's not what we want. We're trying to figure out what wavelengths are coming off of this star, and pixels aren't really very useful. So we need to calibrate our spectroscope. So I'm going to say calibrate. I need to zoom in on this point here, and it says click point number 1. This is the zero order point. I'm going to put my mouse there. It's 73 pixels from the left edge, and I'm going to give it a click. And I've calibrated to one of the points. Now I need a second point to calibrate. So this little dip here is the hydrogen beta absorption line. Most stars have it. It's very dominant. It's pretty easy to find. Some of these other ones are hard to know what they are, but this one is particularly easy. Handy for us, I'll tell you. I'm going to zoom right in on this little section here. And what I want to do is find that lowest point here. Get my mouse to light up. 469 pixels is what it tells me it is. I click on that, and I do tick the checkbox that says that is the hydrogen beta line. That's 4,861 angstroms is what that is. Okay, now having done that, oops. It would help if I hit the apply button. There we go. Now, having done that, I have calibrated my spectroscope. Now, what it's showing me at the bottom here, now you actually see colors. Now, remember, this was not a color camera. This was a monochrome camera. But the computer's saying, yeah, but if it were a color camera, it would correspond to these colors precisely. So it turns out I can use a monochrome camera to detect the spectra. Now, this happened to be a filtered camera. It should not be that dim here and here. Cameras designed for optical use by humans are filtered to mimic human eye responses. Unfiltered cameras for spectroscopy would have been a little bit brighter here. So this isn't maybe the best example, but this is giving me an example, and now I'll tell it to fill it in. Now these are super bright, so this is sort of fake brightness. This is the realistic brightnesses, but that's allowing me to map those colors. Now I can grab here, and I can say, well, show me the hydrogen, the Balmer series for hydrogen. Where's hydrogen? There's hydrogen Balmer series, right? And it's putting these lines on. Now, these are the lines that you saw when Liam put that diffraction grating in front of the spectroscope. You saw the red line? That's here. That's this one right here. You saw that teal blue line? That's here. You struggled to see the other blue line. I showed it to you on the slide. That's here. And I told you there was a violet line. That's here. And these lines you didn't see at all. That's because they're in the UV part of the spectrum. They don't show up to us in human vision, but they do show up to the camera. And that's how this is mapped. Now this is happens to be the spectra of the star Vega. Vega happens to be spectral type A, that's its spectral classification. So if I turn on the spectral classification type A, I can see that actually all these little dips do in fact map all the way across the way. So that's just a quick demo of the sciencey aspect of how this is working. And I am going to go back to my presentation. So with that, this is an object called the Quasar, third Cambridge catalog, item number 273 in the catalog, 3C273, but it's a stellar quasar. So as astronomers are going from star to star to star, they're doing that thing that I just showed you on the screen to say, hey, what's the stellar classification? What's the star made out of? Does it have any planets? All the other fun stuff that I can do. And when they pointed at the quasar, something crazy happens. It doesn't look like a star at all. The word quasar means quasi-stellar. Seems like a star, definitely not a star, right? And the reason it was definitely not a star is because here's the spectra of it, and it doesn't map to anything. Well, didn't map to anything until an astronomer realized so they could not make this fit any elements on the periodic table. So there's something emitting light which is not coming from the periodic table. So they thought, what is in the universe? I mean, there are no gaps in the periodic table. It's not like we're missing elements. And this is made out of something we've never found. We know everything out there. So what could it be? So an astronomer discovered that actually, if he shifted the spectrum over quite a bit to the red end, he could get them to line up. With this mean on the z value of 0.158. That translates to about 16% of the speed of light. That means this object is so far away that the expansion of the universe is expanding, the space between us is growing at 16% of the speed of light. That translates into a distance of nearly 2.5 billion light years away. And you can still see it in a telescope. So this is giving off an absolutely insane amount of energy. Now, I'm not going to go into the whole science of what a quasar really is. It turns out it has to do with the black hole feeding in the middle of a galaxy. But here's the shift. So there's, where the colors should be, and this is where they ended up mapping to. So the hydrogen alpha line is actually mapping off into the infrared spectrum. It's invisible, right? We don't even see it in visible light. So with that, spectroscopy, the gift that keeps on giving. So what can we tell when we use this science? We can tell you the temperature of the star. We can tell you based on the temperature, we can infer the size of the star, which gives us an idea of the mass. Relative motion and velocity, I showed that. The composition, all the elements that are made out of it. If it's a double star, we can tell the orbital period, whether there's the presence of planets orbiting around it. We can also tell the gas pressure of the star and how strong the magnetism is on the star. Does interesting things with the spread of the spectrum.
So Ken, we've got about 4 minutes. So and we have questions. So which you want to do first? Want to do the questions or keep going with the presentation?
Let me just do this one little quick thing. If you grab that penny, because this is the end of it all, and then I'll take all the questions you want. So if you grab that penny, grab the penny now. This is the Hubble Deep Field. Telescope opens up, looks at a piece of sky that they thought was black. Nothing in this piece of sky at all. They did this in 1995, and they got this image with this bat wing. That was because the camera in the upper right corner, they ran out of money, so they had to get a smaller camera. So 3 big field cameras and 1 small camera, and they put them all together, and you get this. They redid it again a few years later. And they got this image. Now here's where the penny comes in handy. Take this penny, if you will. Actually, let me stop my share briefly. So take this penny, if you will, and hold this out at arm's length like this. And with this penny at arm's length, I'm going to restart my share again. Oops, what's wrong share?
Yeah.
Where is my stop share, reshare, wrong screen? There we go. That's the right screen. Okay, there we go. So with this out there, hold this penny at arm's length, and with this out at arm's length, everything that you see in this image is a galaxy. There are just a couple of stars in the thing. And if you look at the penny, every single thing in this image fits at arm's length, not just behind the penny. Look at Abraham Lincoln's head on the penny. Everything in this image fits not just behind Abraham Lincoln's head. Look very, very, very closely at the penny. You're probably going to have to hold it close to see Abraham Lincoln's eyeball. Everything in this image fits behind Abraham Lincoln's eyeball when held at arm's length. These are all galaxies in a piece of sky that tiny, just a few grains of sand across 2.4 arc minutes, about 10,000 galaxies in this image. The red ones are much farther away than the blue ones. The yellow ones are a little bit farther away. This is the spectral shift. This is redshift that you're seeing because the universe is expanding. So this is another application for spectroscopy where you see the colors change because of the visual stretch created by the expansion of the universe. That's all I have for you. Now it's time for questions.
So some questions. First of all, what is the name of the software and the camera that you use for to show the spectrum?
Okay, so the website that you would go to is RSpec, I think it's RSpec-Astro.
Yeah.
If I'm not mistaken, Liam, if you can double check me on that. This camera, any monochrome camera would work. It is best to use a monochrome camera. So this is actually a camera that I bought to be the auto guider for my telescope. And most auto guiding cameras are monochrome, not color. But I wanted it because monochrome cameras don't have filters on them. And so this little diffraction grating is sold at the RSpec Astro website. And so this is an ASI 174 mini, but honestly, any ASI mini size camera would work because it can go in with this little, 1¼ inch eyepiece size thing. So yeah, that's the software and that's the camera.
Another one is, I know for every source you go to, you have to recalibrate the camera, right? Why do you have to calibrate per source?
So you could calibrate onto a gas tube because you know that the gas tube isn't flying toward you or away from you. Okay. But the problem is your telescope probably won't focus on a gas tube unless it's like 100 yards away. But you could calibrate on having done that, you could pick one star. Always calibrate on the same star. They teach beginners to spectroscopy to use Vega as their calibration target. So you notice I use Vega. It turns out it's an easier star because it has a very definite hydrogen beta dip in it, very strong, easy to grab. Some stars are actually kind of tricky to grab. So, grab an easy star, calibrate your software on the easy star, then go for the complicated stars. But there are people that have, there was a supernova that blew up in one of the galaxies, I don't remember which one, and they were able to measure the spectral shift of the light and tell you how fast the gases were being blown out of that. And it turned out to be something like 22 million miles an hour.
Okay, we have time for one more question before we have to end because we have to go into another stream immediately after this.
Nope.
So the one last question is, can you tell the amount of an per element that is created by using spectroscopy?
Can you tell the
quantity?
So what they notice is the percentage of brightnesses, and they can say, well, I have a little of this and I have a lot of that. But that's just what's coming off from the light. I did mention relative to the black body radiation sources. So, one of the interesting things is if a planet passes in front of a star, you actually see two black body curves on the spectroscope, not one, and two different sets of absorption lines. And so you can actually tell these are the absorption lines from the planet's atmosphere of the starlight going through the atmosphere. And now you can tell what's in the atmosphere. So we recently discovered phosphine in the atmosphere of Venus, for example.
Okay, so that's all we have time for tonight. We have to jump to another presentation. Coming up in about 2 minutes or so, if you check back, we have John McGill was actually going to talk to us about taking photographs of NASA's launches, taking photographs of the rocket launches. And then immediately following that, we're going to go into Gordon Hansen talking about the night sky. So please find our links, come join the links, and we'll speak to you shortly. Thank you so much.
All right, thank you.